approaches for coping with load. Sorry. High percentiles of response times, also known as tail latencies, are important because they directly affect user experience of the service. For example, Amazon describes response time requirements for internal services in terms of 99th percentile, even though it only affects 1 in 1000 requests. This is because the customers with the slowest requests are often those who have the most data on their accounts because they have made many purchases. That is, their most valuable customers. It's important to keep those customers happy by ensuring the website is fast for them. Amazon has also observed that a 100 ms increase in response time reduced sale by 1%, and other reports that a 1 second slowdown reduces a customer satisfaction metric by 16%. On the other hand, optimizing the 99.99th percentile, the slowest one in 10,000 requests, was deemed too expensive and to not yield enough benefit for Amazon's purposes. Reducing response times at very high percentiles is difficult because they are easily affected by random events outside of your control, and the benefits are diminishing. For example, percentiles are often used in service level objectives, SLOs, and service level agreements, contracts that define the expected performance and availability of a service. An SLA may state that the service is considered to be up if it has a median response time of less than 200 ms and a 99th percentile under 1 second. If the response time is longer, it might as well be down, and the service may be required to be up at least 99.9% of the time. These metrics set expectations for clients of the service and allow customers to demand a refund if the SLA is not met. Queuing delays often account for a large part of the response time at high percentiles, as a server can only process a small number of things in parallel, limited, for example, by its number of CPU cores. It only takes a small number of slow requests to hold up the processing of a subsequent request, an effect sometimes known as head-of-line blocking. Even if those subsequent requests are fast to process on the server, the client will see a slow overall response time due to the time waiting for the prior request to complete. Due to this effect, it is important to measure response times on the client side. When generating load artificially in order to test the scalability of a system, the load generating client needs to keep sending requests independently of the response time. If the client waits for the previous request to complete before sending the next one, that behavior has the effect of artificially keeping the queues shorter in the test than they would be in reality, which skews the measurements. Percentiles in practice. High percentiles become especially important in back-end services that are called multiple times as part of serving a single end-user request. Even if you make the calls in parallel, the end-user requests still need to wait for the slowest of the parallel calls to complete. It takes just one slow call to make the entire end-user request slow, as illustrated in figure 1 to 5. Even if only a small percentage of back-end calls are slow, the chance of getting a slow call increases if an end-user request requires multiple back-end calls, and so a higher proportion of end-user requests end up being slow, an effect known as tail latency amplification. If you want to add response time percentiles to the monitoring dashboard for your services, you need to efficiently calculate them on an ongoing basis. For example, you may want to keep a rolling window of response times of requests in the last 10 minutes. Every minute you calculate the median and various percentiles over the values in that window and plot those metrics on a graph. The NIB implementation is to keep a list of response times for all requests within the time window and to sort that list every minute. If that is too inefficient for you, there are algorithms that can calculate a good approximation of percentiles at minimal CPU and memory cost, such as forward decay, T-digest, or HDR histogram. Beware that averaging percentiles, i.e. to reduce the time resolution or to combine data from several machines, is mathematically meaningless. The right way of aggregating response time data is to add the histograms. Figure 1.5, when several backend calls are needed to serve a request, it takes just a single slow backend request to slow down the entire end user request. Approaches for coping with load. Now that we have discussed the parameters for describing load and metrics for measuring performance, we can start discussing scalability in earnest. How do we maintain good performance even when our load parameters increase by some amount? An architecture that is appropriate for one level of load is unlikely to cope with 10 times that load. If you are working on a fast-growing service, it is therefore likely that you will need to rethink your architecture on every order of magnitude load increase, or perhaps even more often than that. People often talk of a dicot- dichotomy between scaling up, vertical scaling, moving to a more powerful machine, and scaling out, horizontal scaling, distributing the load across multiple smaller machines. Distributing load across multiple machines is also known as shared NATing architecture. A system that can run on a single machine is often simpler, but high-end machines can become very expensive. So very intensive workloads often can't avoid scaling out. In reality, good architectures usually involve a pragmatic mixture of approaches. For example, using several fairly powerful machines can still be simpler and cheaper than a large number of small virtual machines. Some systems are elastic, meaning they can automatically add computing resources when they detect a load increase, whereas other systems are scaled manually. A human analyzes the capacity and decides to add more machines to the system. An elastic system can be useful if load is highly unpredictable, but manually scaled systems are simpler and may have fewer operational surprises. See rebalancing partitions. While distributing stateless services across multiple machines is fairly straightforward, taking stateful data systems from a single node to a distributed setup can introduce a lot of additional complexity. For this reason, common wisdom until recently was to keep your database on a single node, scale up until scaling costs or high availability requirements force you to make it distributed. As the tools and abstractions for distributed systems get better, this common wisdom may change, at least for some kinds of applications. It is conceivable that distributed data systems will become the default in the future, even for use cases that don't handle large volumes of data or traffic. Over the course of the rest of this book, we will cover many kinds of distributed data systems and discuss how they fare not just in terms of scalability, but also ease of use and maintainability. The architectures of systems that operate at large scale is usually highly specific to the applications. There is no such thing as a generic one-size-fits-all scalable architecture, informally known as magic scaling sauce. The problem may be the volume of reads, the volume of writes, the volume of data to store, the complexity of data, the response time requirements, the access patterns, or usually some mixture of all of these, plus many more issues. For example, a system that is designed to handle 100,000 requests per second, each 1 kilobytes in size, looks very different from a system that is defined for 3 requests per minute, each 2 gig in size, even though the two systems have the same data throughput. An architecture that scales well for a particular application is built around assumptions of which operations will be common and which will be rare, the load parameters. If those assumptions turn out to be wrong, the engineering effort for scaling is at best wasted and at worst counterproductive. In an early stage startup or an unproven product, it's usually more important to be able to iterate quickly on product features than it is to scale to some hypothetical future load. Even though they are specific to particular application, scalable architectures are nevertheless usually built from general purpose building blocks arranged in familiar patterns. In this book, we discuss those building blocks and patterns. Maintainability. It is well known that the majority of the cost of software is not in its initial development, but in its ongoing maintenance, fixing bugs, keeping its systems operational, investigating failures, adapting it to new platforms, modifying it for new use cases, repairing technical debt, and adding new features. Yet, unfortunately, many people working on software systems dislike maintenance of so-called legacy systems. Perhaps it involves fixing other people's mistakes, or working with platforms that are now outdated, or systems that were forced to do things they were never intended for. Every legacy system is unpleasant in its own way, and so it's difficult to give general recommendation for dealing with them. However, we can and should design software in such a way that it will be hopefully minimize pain during maintenance and thus avoid creating legacy software ourselves. To do this, we will pay particular attention to three design principles for software systems. Operability, make it easy for operations teams to keep the system running smoothly. Simplicity, make it easy for new engineers to understand the system by removing as much complexity as possible from the system. Note this is not the same as simplicity of the user interface. Evolvability, make it easy for engineers to make changes to the system in the future, adapting it for an anticipated use case as requirements change, also known as extensibility, modifiability, or plasticity. As previously mentioned, as previously with reliability and scalability, there are no easy solutions for achieving these goals. Rather, we will try to think about systems with operability, simplicity, and evolvability in mind. Operability, making life easy for operations. It has been suggested that good operations can often work around the limitations of bad or incomplete software, but good software cannot run reliably with bad operations. While some aspects of operations can and should be automated, it is still up to humans to set up that automation in the first place and to make sure it's working correctly. Operations teams are vital to keeping a software system running smoothly. A good operation team typically is responsible for the following and more: monitoring the health of the system and quickly restoring service if it goes into a bad state, tracking down the cause of problems such as system failures or degraded performance, keeping software and platforms up to date, including security patches, keeping tabs on how different systems affect each other so that problematic change can be avoided before it causes damage, anticipating future problems and solving them before they occur, i.e., capacity planning, establishing good practices and tools for deployment, configuration management, and more, performing complex maintenance tasks such as moving an application from one platform to another, maintaining the security of the system as configuration changes are made, defining processes that make operations predictable and help keep the production environment stable, preserving the organization's knowledge about the system even as individual people come and go. Good operability means making routine tasks easy, allowing the operations team to focus their efforts on high value activities. Data systems can do various things to make routine tasks easy, including providing visibility into the runtime behavior internals of the system, with good monitoring, providing good support for automation and integration with standard tools, avoiding dependency on individual machines, allowing machines to be taken down for maintenance while the system as a whole continues running uninterrupted, providing good documentation and an easy to understand operational model. If I do X, Y will happen. Providing good default behavior, but also giving administrators the freedom to override defaults when needed. Self-healing where appropriate, but also giving administrators manual control over the system state when needed. Exhibiting predictable behavior, minimizing surprises. Simplicity, managing complexity. Small software projects can have delightfully simple and expressive code, but as projects get larger, they often become very complex and difficult to understand. This complexity slows down everyone who needs to work on the system, further increasing the cost of maintenance. A software project mired in complexity is sometimes described as a big ball of mud. There are various possible symptoms of complexity: explosion of the state space, tight coupling of modules, tangled dependencies, inconsistent naming, and terminology. Hacks aim at solving performance problems, special casting to work around issues elsewhere, and many more. Much has been said on this topic already. 31, 32, 33. When complexity makes maintenance hard, budgets and schedules are often overrun. In complex software, there is also a greater risk of introducing bugs when making a change. When the system is harder for developers to understand and reason about, hidden assumptions, unintended consequences, and unexpected interactions are more easily overlooked. Conversely, reducing complexity greatly improves the maintainability of software, and thus simplicity should be a key goal for the systems we build. Making a system simpler does not necessarily mean reducing its functionality. It can also mean removing accidental complexity. Most Lee and Marx define complexity as accidental if it's not inherent in the problem that the software solves, as seen by the users, but arises only from the implementation. One of the best tools we have for removing accidental complexity is abstraction. A good abstraction can hide a great deal of implementation detail behind a clean, simple to understand facade. A good abstraction can also be used for a wide range of different applications. Not only is this reuse more efficient than re-implementing a thing multiple times, but it also leads to higher quality software, as quality improves in the abstracted component benefit all applications that use it. For example, high-level programming language are abstractions that hide machine code, CPU registers, and syscalls. SQL is an abstraction that hides complex on-disk and in-memory data structures, concurrent requests from other clients, and inconsistencies after crashes. Of course, when programming in a high-level language, we are still using machine code. We're just not using it directly, because the programming language abstraction saves us from having to think about it. However, finding good abstractions is very hard. In the field of distributed systems, although there are many good algorithms, it is much less clear how we should be packaging them into abstractions that help us keep the complexity of the system at a manageable level. Throughout the book, we will keep our eyes open for good abstraction that allow us to extract parts of a large system into well-defined, reusable components. Evolvability, making change easy. It's extremely unlikely that your system requirements will remain unchanged forever. They are much more likely to be in constant flux. You learn new facts, previously unanticipated use case emerge, business priorities change, user requests new features, new platforms replace old platforms, legal or regulatory requirements change, growth of the system forces architectural changes, etc. In terms of organizational processes, agile working patterns provide a framework for adapting to change. The Agile community has developed technical tools and patterns that are helpful when developing software in a frequently changing environment, such as test-driven development, TDD, and refactoring. Most discussions of these agile techniques focus on a fairly small, local scale, a couple of source code files within the same application. In this book, we search for ways of increasing agility on the level of a larger data system, perhaps consisting of several different applications or services with characteristics. For example, how would you refactor Twitter's architecture for assembling home timelines, describing load from approach 1 to approach 2? The ease with which you can modify a data system and adapt it to changing requirements is closely linked to its simplicity and its abstraction. Simple and easy to understand systems are usually easier to modify than complex ones. But since this is such an important idea, we will use a different word to refer to agility on a data system level: evolvability. Summary: in this chapter, we have explored some fundamental ways of thinking about data intensive applications. These principles will guide us through the rest of the book, where we dive into deep technical detail. An application has to meet various requirements in order to be useful. There are functional requirements, what it should do, such as allowing data to be stored, retrieved, searched, and processed in various ways, and some non-functional requirements, general properties like security, reliability, compliance, and scalability, compatibility, and maintainability. In this chapter, we discuss reliability, scalability, and maintainability in detail. Reliability means making systems work correctly even when fault occurs. Faults can be in hardware, typically random and uncorrelated. Software bugs are typically systematic and hard to deal with, and humans who inevitably make mistakes from time to time. Fault tolerance techniques can hide certain types of faults from the end user. Scalability means having strategies for keeping performance good even when load increases. In order to discuss scalability, we first need ways of describing load and performance quantitatively. We briefly look at Twitter's home timelines as an example of describing load, and response time percentiles as a way of measuring performance. In a scalable systems, you can add processing capacity in order to remain reliable under high load. Maintainability has many facets, but in essence, it's about making life better for the engineering and operations teams who need to work with the system. Good abstractions can help reduce complexity and make the system easier to modify and adapt for new use cases. Good operability means having good visibility into the system's health and having effective ways of managing it. There's unfortunately no easy fix for making applicable reliable, scalable, or maintainable. However, there are certain patterns and techniques that keep reappearing in different kinds of applications. In the next few chapters, we will take a look at some examples of data systems and analyze how they work toward those goals. Later in the book, in part 3, we will look at patterns for systems that consist of several components working together, such as the one in figure 1.1. Data models and query languages. The limits of my language mean the limits of my world. Ludwig. Data models are perhaps the most important part of developing software because they have such a profound effect, not only on how the software is written, but also on how we think about the problem that we are solving. Most applications are built by layering one data model on top of another. For each layer, the key question is, how is it represented in terms of the next lower layer? For example, first, as an application developer, you look at the real world, in which there are people, organizations, goods, actions, money flows, sensors, etc., and model it in terms of objects or data structures and APIs that manipulate those data structures. Those structures are often specific to your application. When you want to store those data structures, you express them in terms of a general purpose data models such as JSON or XML documents, tables in relational database, or graph model. Third, the engineers who built your database software decided on a way of representing the JSON or XML or relational or graph data in terms of bytes in memory, on disk, or on a network. The representation may allow the data to be queried, searched, manipulated, and processed in various ways. Fourth, on yet lower levels, hardware engineers have figured out how to represent bytes in terms of electrical currents, pulses of light, magnetic fields, and more. In a complex application, there may be more intermediary levels such as APIs built upon APIs, but the basic idea is still the same. Each layer hides the complexity of the layers below it by providing a clean data model. These abstractions allow different groups of people, for example, the engineers at the database vendor and the application developers using their database, to work together effectively. There are many different kinds of data models, and every data model embodies assumptions about how is it going to be used. Some kinds of usage are easy, and some are not supported. Some operations are fast and some perform badly. Some data transformations feel natural and some are awkward. It can take a lot of effort to master just one data model. Think how many books there are on relational data modeling. Building software is hard enough, even when working with just one data model, and without worrying about its inner workings. But since the data model has such a profound effect on what the software above it can and can't do, it's important to choose one that is appropriate to the application. In this chapter, we will look at a range of general purpose data models for data storage and querying. Point 2 in the preceding list. In particular, we will compare the relational model, the document model, and a few graph-based data models. We will also look at various query languages and compare their use cases. In Chapter 3, we will discuss how storage engines work. That is, how these data models are actually implemented. Point 3 in the list. Relational versus document model. The best known data model today is probably that of SQL, or SQL, based on the relational model proposed by Edgar Codd in 1970. Data is organized into relations called tables in SQL, where each relation is an unordered collection of tuples, rows in SQL. The relational model was a theoretical proposal, and many people at the time doubted whether it could be implemented efficiently. However, by the mid-1980s, Relational Database Management System RDBMS, ES, and SQL had become the tools of choice for most people who needed to store and query data with some kind of regular structure. The dominance of relational databases lasted around 25 to 30 years, an eternity in computing history. The roots of a relational database lie in business data processing, which was performed on mainframe computers in the 1960s and 70s. The use cases appear mundane from today's perspective, typically transaction processing, entering sales or banking transactions, airline reservations, stock keeping in warehouses, and batch processing, customer invoicing, payroll reporting. Other databases at the time forced an application developers to think a lot about the internal representation of the data in the database. The goal of the relational model was to hide that implementation detail behind a cleaner interface. Over the years, there have been many competing approaches to data storage and querying. In the 1970s and early 1980s, the network model and hierarchical model were the main alternatives, but the relational model came to dominate them. Object database came and went again in the late 1980s and early 1990s. XML database appeared in the early 2000s but have only seen a niche adoption. Each competitor to the relational model generated a lot of hype in its time, but it never lasted. As computers became vastly more powerful and networked, they started being used for increasing diverse purposes, and remarkably, relational database turned out to generalize very well beyond the original scope of business data processing to a broad variety of use cases. Much of what you see on the web today is still powered by relational databases, be it online publishing, discussion, social networking, e-commerce, games, software as a service, productivity application, or much more. The title Console, design and development of a secure telehealth video communication system using LiveKit with AI summarization and flexible user access design, was chosen to clearly convey the scope, purpose, and key innovations of the project. Teleconsole emphasizes that the system serves as a centralized platform for telehealth consultations. The phrase design and development indicates that the study covers both the conceptual planning and the actual implementation of the system. Secure telehealth video communication system. Design and development indicates the study covers both the conceptual planning and the actual implementation of the system. Secure telehealth video communication system highlights the platform's primary function, enabling real-time, privacy-focused video consultation, including using LiveKit with AI summarization specifies the core technologies used. LiveKit for encrypted, low latency video communication and AI summarization for automated, privacy-preserving session summaries. Finally, flexible user access design communicates the system's focus on secure, role-based access and controlled session invitations, ensuring that only authorized patients and healthcare providers can participate. Together, the title captures both the technical approach and the system's contributions to secure, AI-enhanced telehealth. What problem your system aimed to solve? Our system addressed two major gaps in current telehealth communication tools. First, most platforms remain basic messenger-style applications with no built-in intelligence. Second, attempts to add AI often risk data exposure or privacy non-compliance. The design and development The Teleconsole design and development of a secure telehealth video communication system using LiveKit with AI summarization and flexible user access design bridges this gap by integrating AI summarization triggered via server-side webhooks that store summaries in Firestore while maintaining strong access control and compliance with Philippines Data Privacy Act. What motivated your group to pursue the topic? During the pandemic, healthcare relied heavily on unstructured messaging, apps lacking privacy and intelligence. We saw the need for Philippine-compliant, AI-enhanced system that supports real-time consultations while respecting confidentiality and access control requirements. Fourth, what makes your system unique compared to existing telehealth platforms? Other apps still rely on direct chat or call features without AI. Secure Chat AI Web automates summary generation of LiveKit sessions via webhook triggered open API calls, storing results securely in Firestore. It also introduced invite-based gated access using signed time-limited JWT links, preventing public access to sessions and transcripts. Who are your intended users and beneficiaries? Our main users are doctors and patients who needed secure, logged, and AI-supported consultation records. Doctors gain time-saving summaries. Patients gain private access without exposing conversations through generic chat apps. Hospitals and clinics benefit from compliant, audit-friendly architecture. Can you describe your system architecture and how each module interacts? Our system follows a server-driven modular design. Front-end Next.js plus custom CSS plus LiveKit components for the user interface and real-time sessions. Backend API routes handle JWT invite validation, AI summarization request, and rate limiting. LiveKit webhooks trigger AI summarization after sessions. OpenAI API processes summaries server-side, which are then stored in Firestore. All communication is secured through signed tokens and HMAC verified webhooks. How does your system ensure that only authorized patients can access consultation sessions? Access is managed through signed, time-limited JWT invite links generated by the doctor. Each link can include optional constraints, country, IP, time, and email. Location, time, and email. Once user expired, the invites become invalid, ensuring only intended recipients can join. Why did you choose Next.js for the front end? Next.js provides React-based framework ideal for full-stack web applications. The API routes simplify back-end integration for token generation and AI calls. The combination allows real-time UI updates with a clean, custom CSS interface integrated with LiveKit components. What database and backend technologies did you use and why? We use Firebase Firestore for structured data storage and Firebase authentication for account management. Firestore provides fast read or write performance and integrates seamlessly with serverless API routes. It stores chat logs, summaries, and invite metadata securely. How did you ensure your system is user-friendly? We designed the interface around LiveKit's modern UI components and clean, readable layouts using custom CSS. We prioritize accessibility through large buttons, clear labels, and real-time sessions feedback indicators. How does your AI summarization feature work? After a LiveKit session ends, a webhook event triggers a backend API route. The API compiles relevant conversation text, sends it to the OpenAI model, and stores the resulting summary in Firestore. This process is automated, secure, and asynchronous to prevent UI blocking. Why is your AI summarization implemented server-side instead of the client-side? Client-side AI models can securely manage API keys and are limited by browser resources. By performing summarization on the server, we keep credentials secure, apply rate limiting, and maintain consistent processing. The backend is protected through HMAC verified webhooks and signed API routes. What are the limitations of your AI summarization module? Summaries rely on the quality of input transcripts. Since summarization runs post-session, users must wait briefly before seeing the results. Also, model accuracy depends on the text clarity and may omit contextual nuances. How does your system comply with the Philippine Data Privacy Act of 2012, RA 10173? We implement transparency. Users are informed before data use, legitimate purpose. AI summaries are for authorized consultations only. Security. All access uses signed JWT tokens and verified webhooks. Data minimization. Only essential conversations metadata is stored. Raw video or audio are not retained. All this align with RA 10173 compliance principles. 15. What encryption or security measures protect user data? We use transport layer security TLs for all communications, HS256 signed JWTs for access tokens, and HMAC verification for webhook requests from LiveKit. Additionally, we implement per IP rate limiting and input sanitation to mitigate abuse. How do you prevent unauthorized access or repeated brute force invites? Our backend tracks invalid attempts and applies IP-based rate limiting. JWT invites expire automatically after a set duration and cannot be reused. Optional country and browser matching add further protection. What testing process did you perform? We use manual functional testing and API endpoint scripts to verify authentication, webhook signing, and rate limiting. Local load tests validated that summary generation and invite validation work under concurrent sessions. How did you evaluate the usability and performance of your system? Performance was measured by monitoring Firestore response times, token validation latency, and AI response duration. Qualitative feedback from pilot testers, students simulating doctor-to-patient sessions, guided interface refinement. What improvements or features would you like to add? Future updates may include real-time AI summarization previews, multi-language support, and doctor analytics dashboard. We also plan to explore federated summarization and blockchain-based audit logs for immutable access records. What do you think is the main contribution of your study? We demonstrated a secure, webhook-driven AI summarization workflow suitable for healthcare communication under Philippine data privacy law. It bridges the gap between AI automation and compliance, offering a forward-looking framework for privacy-aware telecommunication systems. Watashi, English meaning I or me. Example sentence, I am a student. Sentence in Romanji, Watashi wa gakusei desu. Romanji, anata. English meaning you. You are my friend. Anata wa watashi no tomodachi desu. Romanji, kare. English meaning he or him. He is tall. Kare wa sega takai desu. Kanojo, English meaning she or her. Example sentence, she is kind. Sentence Romanji, Kanojo wa shinsetsu desu. Romanji, watashi tachi. English meaning we or us. Example sentence, we are classmates. Watashi tachi wa kurasumeitu desu. Romanji, anata tachi. English meaning you, plural. Example sentence, you all are welcome. Anata tachi wa you koso desu. Romanji, karera, meaning they/them. Example sentence, they are teachers. Karera wa sensei desu. Romanji, kanojo tachi, meaning they or them. Example sentence, they are friends. Kanojo tachi wa tomodachi desu. Romanji, kazoku, meaning family. Example sentence, my family is big. Watashi no kazoku wa uki desu. Romanji, haha, meaning mother. Example sentence, my mother cooks. Haha ga ryuri shimasu. Okasan, meaning mother. Example sentence, mother is kind. Okasan wa shinsetsu desu. Romanji, chichi, meaning father. Example sentence, my father works. Chichi wa hatarakimasu. Romanji, otosan. meaning also father but in polite way. Example sentence, father is strong. Otosan wa tsuwoy desu. Romaji ani, English meaning older brother. Example sentence, my older brother studies. Ani wa benkyu shimasu. Romaji oni-san, meaning older brother, polite. Example sentence, older brother is tall. Onisan wa sega takai desu. Romaji ane, meaning older sister. Example sentence, my older sister is kind. Ane wa shinetsu desu. Romaji onisan, meaning older sister. Example sentence, older sister studies. Onisan wa benkyu shimasu.